Rian. I'm here today to present two articles. One is about the automatic CAD design of the occlusal morphology of crowns, and the other one is related to digital byte registration. Now, let's start with the first one. The title of the study is Fully Automatic CAD Design of the Occlusal Morphology of Partial Crowns compared to dental technicians' design. A fundamental consideration in restorative dentistry is the occlusal design, which is not only important for mastication but also for the stability of the entire stomatognostic system. Currently, restorative dentistry is transitioning from manual to computerized fabrication by means of CAD/CAM devices. However, it still has a gap that needs the help of a human operator, which is designing the occlusal surfaces. So, more advanced CAD software systems try to fill this gap by using algorithms to fit the occlusal to static or dynamic byte registration. However, there remains a desire for a CAD system with fully automatic occlusal surface resolution. So many studies have introduced a biogeneric tooth model which is able to assume an entire occlusal surface based on a 3D data library of hundreds of scans of intact human posterior teeth. However, the question still remains whether this software can compete with well-trained dental technicians in occlusal designing. The aim of this study was to compare the occlusal morphology of reconstructions made by dental technicians with reconstructions made by the biogeneric tooth model. Five participants from the age of 21 to 33 years who have intact tooth surfaces were involved in this study. Polyester impressions were made for both jaws, and then stone replicas were fabricated. After that, the occlusal surfaces of the molars were scanned with a 3D scanning device. Next is the simulation of inlays or lace preparation on the stone replicas. For this, one molar tooth was randomly chosen in each subject, and at least one cusp was left untreated during preparation. For fully automatic reconstructions, byte registrations of the antagonist were taken with a scannable vinyl polysiloxane registration material. The prepared teeth and their antagonists were scanned with an optoelectronic intraoral camera. The obtained models were virtually trimmed and preparation margins were set. Then, reconstruction data were saved as STL format and XV format files. Conventional reconstructions were performed by five well-trained dental technicians, and each waxon models were scanned with the above-mentioned 3D scanner, and the data was saved in the same way as described before. This figure shows the scan data obtained by different means. Figure A represents the original tooth surface. B is for virtual CAD reconstruction, and C to G are scans of waxon models by five dental technicians. As we can see in the figure, it is obvious that the reconstructions clearly differ from each other even at first sight. For 3D similarity measurements, all reconstructions were superimposed with their original surface according to the best fit method by the program Match 3D 2.5. These figures are representative cases of difference imagery displaying column-marked local 3D distances. It was calculated within the datasets by evaluating distances point by point in three directions. The areas we can see as green represent low differences, while the red or blue area account for high differences. To measure 3D similarity, the shape similarity value was calculated, which is the sum of the positive volumetric deviation and the absolute negative volumetric deviation divided by the surface area of the difference image. In mathematical theory, this value corresponds to a L1 distance metric in k-dimensional vector space. If the obtained SSV is high, it means the superimposed surfaces are more dissimilar and vice versa. With this measure, similarities between computer-based reconstructions and corresponding nature tooth forms, and similarities between reconstructions made by the technicians and corresponding nature tooth forms were calculated. Statistical analysis was performed with SPSS-14, and all significant differences were detected at a 95% confidence level. The null hypothesis was that there is no statistically significant difference concerning the shape similarity measure between samples, and it was tested by student t-test. Subgroup analysis was performed by Vonay Anova with post-hoc LSD test. As a result, in 22 of 25 cases, the CAD reconstructions were closer to the original situation than the technician's reconstruction. Moreover, as we can see in this graph, the mean SSV of 310 micrometer for the technician's reconstructions was significantly higher than that of 222 micrometer for CAD reconstructions. This is the graph showing the total volume difference of all 25 samples. Only in 3 out of 25 samples of the technician's reconstruction showed a low value of the SSV than the CAD reconstruction. According to the SSV, technician number 3 of case 2 and technician number 2 and 4 of case 5 were able to design more natural tooth morphology. In this study, unlike calculating the standard deviation, the SSV includes the deviations in a linear way, so it doesn't overestimate outliers with quadratic terms as well as reducing errors which may arise from differences on steep inclines or measurement errors made by optical scanners. Higher SSV variances of the occlusal surface, waxed up by the dental technicians, reflect the individuality of wax-up parents. However, in some single cases, a conventional reconstruction can produce a more natural tooth form. There are some limitations to this study. The first one is that it couldn't provide direct information on the aesthetical fit of the reconstructed crowns. The second one is that proximal, buccal, and oral surface were not taken into consideration. Next is that the point of critique could be that functional aspects are not explicitly assessed. This is the conclusion of the study. Within the limitations of this study, a fully automatic editing system can be at least as good as conventional workshops made by dental technicians with regard to the design of naturally shaped occlusal inlay on lay surfaces. In the future, the automatic design of complete single and multiple tooth restoration could become possible. Algorithms that can derive the morphology of a tooth from the shape of its neighboring and antagonistic teeth are necessary. Then I will move on to the second article. The title of the study is "A New Technique for Testing Accuracy and Sensitivity of Distal Bite Registration: A Prospective Comparative Study." With technological advances, orthodontic applications have become increasingly digital and traditional impression techniques have been replaced by intraoral scanners. Nowadays, iOS devices are capable of identifying and recording interocclusal relationships. Interocclusal registration could be recorded directly in the mouth when the teeth are in the maximum intercostal position, or distal models could be manually aligned in the iOS device software. There are a limited number of studies testing the accuracy of interocclusal recordings of iOS devices. However, these previous studies did not evaluate all bite registration surfaces as a whole. In this study, the occlusal recording accuracy of the iOS device was tested by a 3D evaluation of all contact surfaces. The aim of the study was to determine the accuracy and sensitivity of an occlusal bite obtained with an intraoral scan device and to compare virtual occlusal recording to traditional methods. 40 patients with Class 1 malocclusal were included in the study. Class 2 and Class 3 patients were excluded from the study due to the possibility of undeniable anterior thickness of the occlusal record. IOR were collected using 4 different bite registration methods for each patient. 3 were done by traditional means and 1 was by virtual means. So, this results in a total of 160 IOR for 40 patients, which were divided into 4 groups. 3 qualitative VRMs were used for groups 1, 2, and 3 respectively. In these 3 traditional bite registration methods, the patients were asked to close their mouths in the maximum intercostal position and all teeth were air-dried before the materials were inserted. After ensuring that all 3 IORs were perfect, it was first air-dried, then scanned by an iOS device and converted to a 3D digital IOR in the STL format. The figure shown in the slide presents digitalized bite registration of 3 traditional and 1 virtual registration method. To construct a virtual bite registration first, all the teeth were air-dried, then the lower and upper distal models of the patients were obtained using the 3-shape Trios device. The left and right buccal areas were also scanned when the teeth were in MIP to record the IOR of the distal models. The models were automatically articulated by the device. The articulation result was compared with the intraoral teeth relationship, so its accuracy was verified. Precisely aligned models were imported into the appliance designer software. Step-by-step creation of the virtual byte registration is shown in the figures A to D. First of all, the upper teeth were covered with a virtual bar, and then virtual bar edges were reshaped according to the borders of the teeth, as shown in figure B. After that, the models were brought into articulation and imprints of the upper and lower teeth were created on the virtual bar. Finally, the VBR was saved in an STL format and exported. Next is superimposition stage. Three traditional and one virtual 3D digital IORs were transferred to the Geometric Control X software. Group 3 IORs were used as a reference in all 3D superimpositions because of its superiority to other materials. This figure shows the process of 3D superimposition. The reference IOR was superimposed with the other IORs separately using the local best fit algorithm. Surface deviations resulting from the overlapping were qualitatively demonstrated by color histogram as shown in the figure. For perfectly aligned areas, we can see as green color and it is presented as red color for positively positioned areas and as blue color for negatively positioned areas relative to the reference model. As we can see in the figure, only contact regions from the first molar to canine were selected bilaterally for evaluation. The reason is to avoid the result then adversely affected by the uncontrollable thickness of the impression materials in the anterior region. Moreover, geometric control X automatically converts surface deviations into quantitative data. The sum of PPA and MPA gives the OTA value. The OTA describes the total deviation as a percentage. The PPA and MPA values represent the negative or positive distribution of the total deviation. Mean values and standard deviations of all parameters were determined using the SPSS22 package program. Cross-cut release and post-hoc Temhan tests were used to compare the data between the groups. This table shows mean value of the parameters and comparison of findings among groups. There was a statistically significant difference of MPOS between Group 1 and the other groups. This meant that in some regions of IOR, waxes were slightly thicker than C-type silicones and VBRs. The values of the PPA and MPA indicate the direction of the difference in thickness. The distribution of PPA values between the groups was 31.9% for Group 1, 16% for Group 2, and 7.8% for Group 4. The only Group 1 shows statistically significant differences from other groups. This is the discussion of the study. The different location and size of contact points on the same digital models can be seen in different software. This is because each software brings the models in MIP with its own unique algorithm. In this study, the results revealed that there was an average deviation of 70 to 80 meters between the reference groups and the study groups. These findings were consistent with The finding on another study where reverse engineering software was used and detected an average of 69 meters deviation. In this study, a more sensitive and more holistic method was used than previous studies. Not only the contact points, but also proximities or occlusal surfaces were evaluated. However, the findings that the VBR was as reliable as traditional IORs were consistent with the results of previous studies. This was an indicator of the accuracy of new byte registration evaluation technique. There are some limitations on this study. Byte first generated by patients could be a confounding factor in the 3D comparison of byte registration method. So, one limitation of this study was the fact that the complete standardization of the byte first of the participants could not be achieved quantitatively. Another drawback of this new technique was the need for each IOR to be digitized, so the process was a bit time-consuming and sensitive. Additionally, no retest was performed for the new technique used in this study. So, within the limitations of the study, it was concluded that virtual byte registrations could safely be used as an alternative to conventional VRS and that the performance of wax as a byte registration material was far behind other methods. That is the end of my presentation. Thank you so much for your kind attention.